Good afternoon, ladies and gentlemen. Good afternoon, Marina Nikolaevna. And well, thank you for the introduction. And let me first thank the organizers for giving me this opportunity. It's a big honor to give a talk at this conference, especially for me because in my PhD thesis many years ago, I think about a quarter of the references were dedicated to the rare earths, and well, I'm not sure if I have managed to contribute to the field a lot, but at least I need to confess that I've spent years explaining, at least for myself, how certain things work, as described in that great number of the papers. Okay, and yes, special thanks to the organizers to give a chance for a purely theoretic talk just before the boat trip. So I'll try to fit within my 20 minutes, even though I think we are just a little bit ahead of time. Okay. Okay. Well, in this audience, I don't think I need to spend too much time for the introduction. It will be about all the photoluminescence since its theory. I will not speak precisely of certain things. That would be some light emitters with whatever transition structure. And well, it's usually the gas particles that are embedded into a host material, most likely to be a continuous medium host, kind of fully or mostly transparent towards the incident light. And yes, since if you have an external light source, you illuminate it with the photons and give birth to a lot of the electronic excitations in the gas particles, and since the excitations decay, they give birth to the secondary light, which we know as photoluminescence. And so that has many aspects, and I will speak about one important in some number of cases. So if we look for the photoluminescence, it's important sometimes to tell the difference between the emission from an ensemble of the gas particles and the emission from single particles that can be registered individually. All right, so if we speak about the emission from the ensemble, from a collection of the particles, I want to draw attention to this important paper for my research. And well, since this symposium is in the memory of a great scientist, Fyodor Feofilov, it's also the memory of Sergei Petrovich, and his work that inspired a direction in our research as well. And that's when they showed that there is a change in the emission rate, or this picture that made the connection with some theoretical formula that explained a very well-known fact that if the gas particles are inside the material with the refractive index, then the higher the refractive index of the host material is, the brighter the photoluminescence is, and so the shorter the radiative lifetime of the gas particles. Okay, and so this dependence have been measured in many cases for the ensembles, and there were different theoretical approaches to explain this nonlinear dependence. I think that the most successful were to use some of the corrections to the lifetime. And the change in the lifetime is broadly known as the Parcels effect. And sometimes it is the Parcel effect is used in the literature as an explanation of a sharp rise of the photoluminescence intensity, without taking into detail for the reasons for that. Okay, but that is the effect that I'm going to speak about today, and one of the methods to describe it theoretically. Okay, well, the theoretical curves here do not seem to fit well the results, the experimental points that I will also show another picture which explains the case maybe in a little bit better or more comprehensible way. And so here is the rising refractive index of the host. Well, that's basically taking as at the frequency of the radiation. And with the experimental dots where these are the europium ions in glasses and prepared for the same conditions, where the glassy material, host material, was prepared in such a way that there was a number of experiments when the host material had different refractive index. And the measurements demonstrated the expected trend, so there's a nonlinear falling of the excitation lifetime. Okay, and now the theoretical lines, the curves show that if you take the generalized parcel factor, which should generally be understood as in terms of the density of the final states for the emission, or the fact that with the higher values of the refractive index, the light propagates slowly, and that is the reason for the higher density of the states, and according to the parcel effect, gives a rise of the luminescence intensity with a shorter excitation lifetime, of course. Okay, but this explanation, if we take into account only the circumstance, usually explains just a part, just a fraction of the experimental curve, not giving a good agreement and either end of the experimental range of the data. So what have been done in the literature was the introduction of another factor to the correction to the lifetime, which is the ratio of the local field in the continuous medium, organized by a continuous medium, to the Maxwellian field, which can be estimated according to the classic theory for the host material with certain dielectric properties. Okay, so the ratio must somehow be introduced in most cases phenomenologically, or use the model to give the best fit for the experimental data. And so if this is done, then the curve that explains this falling excitation lifetime usually can give very good agreement with the observed intensities. Okay. Now, there is also a little connection of our interest to this work was inspired by our interest in the single photoluminescing particles, and that is now a routine to see the photoluminescence signal from single organic molecules or nanocrystals and some other particles. So it's if such a fact, the change in the lifetime is applicable to single emitters, then it is obviously a good chance to see how the host may be changing locally, because again, nowadays it's a routine if someone is collecting light from individual single emitters, and we can restore the coordinates at least in one plane, and that's just a good chance to perform some mapping of the dielectric if the dependence on the index of refraction of the refractive index is the same as for the ensembles, then there's a chance to perform some mapping of the dielectric distribution. But in contrast to the ensemble measurements, the single emitter measurements give the distributions of the lifetimes from one particle to another. And well, if you collect them back into ensemble, any distribution, any dispersion of the lifetime would automatically suggest that there can be a non-exponential decay from the big group. But on the contrary, if we approximate this with a normal distribution and take the sigma as the width, then the simple integral says that yes, indeed, with the dispersion of the lifetimes for the ensembles within homogeneous broadening, we would expect some tricky power law decay. But for the sigma values that were indeed registered in such experiments, the decay, I mean, the visual difference from the exponential law is minimum. So that's only about the single emitter experiments to register the difference. Okay, now let me announce before I show you the formulas, the results that we have at hand at the moment. Since that's the quantum kinetic theory, that's all about deriving accurately or with very special care a master equation for a density matrix that describes a light emitter. And of course, it contains the rate of emission, which, if everything is done correctly, should be something that does describe the change of the emission rate or the excitation lifetime of a gas particle in a host. Okay, so these are the general, that's the general formula for the T1 or the excitation lifetime. And it has been calculated for the host medium, which is weakly absorptive. It has a small negative term for the complex dielectric function. Okay, and yes, it does really depend on the rates of the emission rate, and yes, the radiative shift in the vacuum. But anyways, this formula is general, and it is applicable for the absorptive host media as well. Okay. Now, the thick blue line is the result that we have, and this is the comparison with the other models. That's our fitting lines for the data collected from the literature about the rare earths, as well for the semiconductor nanocrystals here. And the other curves demonstrate the competing theories, or mostly phenomenological. And the general thing here is because the way the emitters, the gas emitters, are inside the host material, the question of the host is a very complicated one, because in addition to just knowing the properties of a continuous bulk material, which is the host, it must something must be done about counting for the circumstances that are in the very near vicinity of the thing. So the way it is embedded inside, and so we are, if we answer, we just give the answer to just only some part of the questions. All right, but anyways, if we so the curves that we have might not seem the best, but if we go back, if we bring back the error bars, then for both the quantum dots and for the rare earths, if we do not compare it with other models, at least the theory that we developed gives some, you see, good agreement. Okay, now for about the theory itself, you know, this is the very well familiar master equation for a density matrix of a two-level emitter, say that, and it has the damping term, which traditionally has two parts: the Lindblad operator that describes the radiative damping, and the dephasing operator in case of the dephasing effects. Okay, there are many hierarchy methods used, well, some from the Heisenberg picture using the density matrix formalism, and we have developed one separate, but they are known generally to give given a path to derive the damping terms without using any phenomenology. Okay, so for our method, we look at a huge many particle system that contains the particles that describe the light emitters. There are also the subsystem that the infinite number of subsystems that each of where each subsystem describes a photonic mode, the particles that describe the medium, the host medium. The difference is that the emitters have the transitions resonant to the incident photons, and the medium is polarizable against the incident field, but with all the transitions laying far off resonance from the excitation beam. And you can also, we may include some other objects, and the only thing that is stated here is the interaction of the solid part of the material particles with the photonic modes, which may be written in terms of either the general formula or using the electric dipole approximation. Okay, so all material particles, whatever they are interacting via the photonic modes. Okay, now such a huge system is described with a full density matrix, which is known to obey the von Neumann equation, where the full energy operator that you need to write in it is in a very conventional and simple form. Now, for the reduced density matrix, that we use the property of the reduction, where we take the partial trace of the particles we're not interested in, and we get a density matrix for some subsystem. And the reduced energy operator, of course, contains the energies and the interactions between the particles that belong to the subsystem of our interest. So, taking the reduction property and applying it to the von Neumann equation, we may get this general formula for the equations for the reduced or the partial density matrices. And here is the example of the three type. This is for the material particles, for the field modes, and for the two particle. These are single particle matrices and the two particle matrices. And of course, it goes forever until you end up with a density matrix that describes entirely the full ensemble. Yeah, except one, but the number is infinite because there's an infinite number of photonic modes. Okay, then there's a thing that for the many particle matrices, we make a substitution with the correlation matrices, where we take many particle density matrix as a superposition of the factorized and non-factorizable forms for the three things. These are all the permutations, etc. And substituting this way, we come to an endless hierarchy of equations written for the single particle or for the single particle density matrices and for the so-called correlation matrices. So the entire system, the entire hierarchy is absolutely equivalent to the von Neumann equation and works no good. So it must be truncated somehow using some criteria for getting rid of or not taking into consideration any of the correlation matrices that take too many particles in it. Okay, so that's non-formula explanation. What it has the particle, a lot of particle equations, the photon mode equations for the correlation matrices, etc. Okay, and what we finally do, if to get the master equation, you have to solve formally make this formal solutions, the integrals for the other matrices that the density matrix of an emitter you are interested in, it depends on. You introduce it there, and if then with a lot of work of getting rid of the time integrals to come back to something which is also very familiar. Here is the example of the system of the density matrices for a two-level atom. But in case the subsystems are many and some particles describe guests and some host things, that the same procedure, if taken carefully, brings you another a master equation in which all the parameters
something happened. We do not hear you.
naturally without any things to okay, I have one final slide here, and just the different models of how you take the spatial averages and taking it either the two different type these problems models, and you get either the Lorentz local field or the Ansager field local field factor for the continuous medium. Right. So the master equations has these things. The rate or the lifetime, which is effective and calculated for some of particular situation. And now the implementation of so this kinetic theory and give the parcel factor and the local field correction all together. And now the implementation of the results, please visit the future talks. One is this, given by Andrei Naumov, and explaining how the mapping that I mentioned earlier was prepared. And so that uses the results of the developed theories for the local field correction to the lifetime. And the hierarchy method for the cooperative systems is also posted by Katerina Smirnova. Please visit. Thank you.